Hello everyone, welcome to a new problem. So we have z is a complex number. Show that modulus of z minus real part of z is less or equal to 1/2 is equivalent to z equals ac, and modulus of c bar minus a is less or equal to 1. Of course, real of z is the real part of z. That is, if z is equal to x plus I times y, where x is a real number and y is also a real number, then real z is x. Of course, y is called imaginary part of z. But we don't need the imaginary part, so we will not use this notation. And I, of course, is the imaginary unit. We also call it the square root of -1. So we also use z bar, like we see here, c bar. So z bar, that's the conjugate of z. And it's defined as x minus iy. So z bar is the conjugate, and we obtain it by changing the sign of the imaginary part, y. The modulus of z is the square root of z times z bar. Okay? And if we write z as x plus iy, so it's square root of x squared plus y squared. Now, you can, as usual, pause the video and try to solve the problem. But to prove this equivalence, we will do it in two parts. We'll prove the first implication, and then we'll prove the reciprocal. That's how we're going to solve the problem. But first, before doing that, I would do a calculation here. So this c bar minus a, as c is a complex number, of course, and a also is a complex number. So c minus a squared is equal to c minus a, c bar minus a, times the conjugate of this number, which is c bar minus a all bar. But we can distribute this conjugate sign over this difference, so it gives us c bar minus a times c minus a bar. And if we expand this product, we have c bar minus ac minus c bar a bar, so a bar c bar plus, that's minus, that's a bar. C bar, that's modulus of c squared. A bar, that's modulus of a squared, and then minus ac plus a bar c bar, which is a c bar. And this is exactly modulus of c squared plus a squared minus 2 times real of ac. That's real z. Because, of course, if z is equal to x plus iy, and z bar, of course, is equal to x minus iy, then z plus z bar over 2 is equal to x plus iy plus x minus iy. Of course, we all over 2. So iy minus iy will cancel out, and so we have 2x over 2, that's x, which is real part of z. So the real part of z is always equal to z plus z bar over 2, and then z plus z bar is equal to 2 times real of z. That's what we did here. So we have this calculation, we'll need it later. So let's prove the first application. That means z is a complex number and such that absolute value of z minus real part of z is less or equal to 1/2. Of course, any number z can always be written as a product of two other complex numbers. This is a completely valid equality. So what we need to do is to find out that modulus of c bar minus a is less or equal to 1. The equivalence says that there exists a and there exists c in the complex set, so that we have these two relations. So let's find some condition on a and c so that this inequality holds. We have c minus a squared is less than 1, means that c squared plus a squared, modulus of c squared plus modulus of a squared minus 2 real of z is less or equal to 1. But that's what we need to show. But we have z minus real part of z less or equal to 1/2 applies if we replace z by ac. So we have modulus of ac minus real part of ac is less or equal to 1/2. So we will multiply both sides by 2. So we have 2 times modulus of a modulus of c, since this can be parted as a product of 2 modulus. And since we multiply by 2 both parts, we have this inequality here. Now we must show that if this is true, this is also true under some condition. Let's modulus of a equals modulus of c equals, of course, square root of modulus of z. Then modulus of a squared plus modulus of c squared is equal minus 2 modulus of a modulus of c is equal to modulus of a minus modulus of c squared. But that would be equal to 0. Since a modulus of a equals modulus of c, this is equal to 0. That would imply that modulus of a squared plus modulus of c squared is equal to 2 modulus a modulus c. So, since we have this, if we return to this relation here, so this will become 2 times modulus A modulus C will be replaced by A minus 2 real part of AC is less or equal to 1. And that means exactly that modulus of C bar minus A is less or equal to 1. So if we have this inequality here, then there exists, of course, A and C in a C complex set, so that modulus of A is equal to modulus of C, and of course, since the Z is the product of both, so this modulus here should be the square root of modulus of Z. Now let's prove the reciprocal. If Z is equal to AC and modulus of C bar minus A is less or equal to 1, then modulus of Z minus real part of Z is less or equal to 1/2. So this part means C bar minus A is less or equal to 1 is equivalent, in fact, to C bar minus A squared is less or equal to 1 squared, since everything is positive. That means that A squared, modulus of A squared plus modulus of C squared minus 2 real part of Z is less or equal to 1. Since this is this. From the beginning, prove that C bar modulus of C bar minus A squared is equal to this. So this is it. But we know that modulus of A minus modulus of C squared is positive. That means that A squared plus modulus of C squared minus 2 modulus A modulus C is greater than 0, and that means that modulus of A squared plus modulus of C squared is greater than 2 modulus A modulus C. If we add minus 2 real part of Z, we will find out that modulus of A squared plus modulus of C squared minus 2 real part of Z is greater than 2 modulus A modulus C minus 2 real part of C. Then since A squared plus modulus of A, or absolute value of A squared plus absolute value of C squared, is minus 2 real part of Z is less or equal to 1. So this is less or equal to 1, and it is bigger than or greater than this part here. So that means, or let's say here, since we have this, that means that this 2 modulus A modulus C minus 2 real part of Z is less or equal to 1. So we will divide by 2. That means modulus of AC minus real part of Z is less or equal to 1/2, and this is, since Z is equal to AC, that's modulus of Z minus the real part of Z is less or equal to 1/2, which ends the proof. Thank you very much for watching, and I hope to see you in the next video. Thank you very much.